systems are highly vulnerable to space weather, with solar flares and coronal mass ejections posing significant threats. High-energy particles and electromagnetic radiation from these events can interfere with the radio wave satellites use to communicate with Earth. Disruptions caused by solar storms can affect television broadcasts, internet services, and GPS navigation. These interruptions create cascading effects in industries reliant on real-time data, including aviation and maritime operations. For instance, navigation systems may become inaccurate during solar storms, leading to delays and safety concerns. The physical infrastructure of satellites also faces risks from charged particles during solar storms. These particles can accumulate on satellite surfaces, causing short circuits and damage to onboard systems. Operators often place satellites in safe mode during heightened solar activity to protect sensitive components. While this precaution minimizes damage, it halts the satellite's operations temporarily, impacting services like telecommunications and weather forecasting. Prolonged space weather events can accelerate satellite degradation, weakening materials, and reducing solar panel efficiency. Such degradation shortens satellites' lifespans, raising economic and operational concerns as the world increasingly depends on satellite networks. Past geomagnetic storms have caused millions of dollars in satellite damage, highlighting the stakes involved. To counter these risks, advanced monitoring systems and better satellite designs are critical. NASA and NOAA track solar activity to provide early warnings, helping operators prepare. Radiation-hardened materials and enhanced shielding are also improving satellites' resilience, ensuring uninterrupted global connectivity despite space weather challenges. Power grid failures. Power grids are among the most vulnerable systems to the effects of space weather. Geomagnetic storms caused by solar activity can generate geomagnetically induced currents in the Earth's crust. These currents infiltrate power grids, overloading transformers and disrupting their functionality, leading to widespread blackouts, as seen during the 1989 geomagnetic storm that caused a 9-hour outage in Quebec, Canada. The infrastructure of power grids experiences significant stress during geomagnetic storms, especially transformers, which are crucial for electricity distribution. Overheating and physical damage from induced currents can cause transformer failures, increasing the risk of cascading outages that can spread across regions. The risks are heightened in polar regions, where geomagnetic effects are stronger due to proximity to Earth's magnetic field lines. Power grid failures have far-reaching consequences beyond immediate outages, impacting essential services like hospitals, communication networks, and transportation systems. Prolonged disruptions can result in financial losses and safety risks for affected populations. The integration of smart grids and renewable energy sources adds complexity, amplifying the challenges of maintaining grid stability during geomagnetic storms. To mitigate these risks, scientists and engineers focus on real-time monitoring of solar activity and geomagnetic conditions, providing utility operators with early warnings. These alerts allow preventive measures such as adjusting grid load or shutting down vulnerable systems to be implemented. Advancements in transformer design and protective technology, like geomagnetic storm detectors, further enhance grid resilience, ensuring reliable electricity despite space weather challenges. Satellite damage and orbital hazards. Satellites, essential for modern communication and navigation, are highly vulnerable to space weather. Energetic particles from solar storms can penetrate a satellite's shielding, causing malfunctions in electronic components and disrupting services like GPS navigation, internet access, and global communications. A significant example occurred in 1994, when a major solar storm caused multiple communication satellites to malfunction, leading to widespread service outages. Radiation from solar activity further challenges satellites by degrading construction materials over time. This exposure weakens solar panels, reducing power efficiency and shortening operational lifespans. Intense solar events can also trigger damaging electric discharges within satellites, potentially rendering them inoperable. These risks highlight the need for rigorous testing and innovation in satellite design to ensure resilience against space weather. Geomagnetic storms exacerbate the orbital debris problem by expanding Earth's atmosphere, increasing drag on low Earth orbit satellites and debris. This alters trajectories, heightening collision risks, and raising the possibility of a cascading event known as the Kessler syndrome, which could make orbital zones unusable. With thousands of satellites already in orbit and many more planned, these risks grow increasingly urgent. To mitigate these threats, engineers use advanced shielding and error correction systems to counteract radiation effects. Real-time monitoring of solar activity allows operators to adjust satellite positioning or place them in safe modes during high-risk periods. Collaborative initiatives like space traffic management systems monitor satellite and debris movements to prevent collisions. By integrating these measures with innovative designs and predictive technologies, we can protect satellites and the critical services they provide to our interconnected world. Impacts on aviation. The aviation industry is significantly affected by space weather, especially during periods of heightened solar activity. Solar flares and coronal mass ejections release intense radiation that can penetrate Earth's atmosphere, posing risks to high altitude and polar flight routes. Aircraft flying at high latitudes where Earth's magnetic field offers less protection are particularly vulnerable to increased radiation exposure, which can slightly elevate long-term health risks for passengers and crew. Communication systems on board aircraft are also susceptible to space weather disturbances. High-frequency radio waves, crucial for communication with air traffic control, can be disrupted by solar flares causing ionospheric disturbances. Such disruptions force reliance on alternative channels, leading to delays and operational challenges, especially where backup systems are limited. Additionally, these disturbances can complicate coordination in remote regions, increasing operational risks. Space weather can also compromise navigational accuracy, as aircraft depend heavily on GPS for routing. Ionospheric turbulence during geomagnetic storms degrades GPS signals, resulting in location inaccuracies. To mitigate these risks, aviation authorities collaborate with space weather monitoring agencies to receive real-time alerts and forecasts. Adjusting flight paths during solar storms and advancements in resilient communication technologies ensure passenger safety and operational efficiency. Interruptions in radio communications. Radio communication systems, the backbone of global connectivity in many industries, are particularly vulnerable to disruptions caused by space weather. Solar flares and coronal mass ejections release intense bursts of X-rays and ultraviolet radiation, ionizing the Earth's upper atmosphere and disrupting the ionosphere, which reflects high-frequency radio signals. During severe space weather events, this can lead to radio blackouts, disrupting HF transmissions critical for aviation, maritime operations, and military activities, leaving many regions without reliable communication. The aviation sector, especially on transoceanic and polar routes, relies heavily on HF radio for communication between aircraft and ground control. Solar flares or geomagnetic storms can cause sudden loss of these channels, necessitating rerouting or flight delays, and reducing situational awareness for pilots and controllers. These disruptions are especially critical in polar regions where alternative communication systems may also face interference due to space weather. Maritime operations also face risks, as ships depend on HF signals for weather updates and coordination, leaving vessels without crucial navigation information during blackouts. Mitigation efforts focus on predicting space weather events and enhancing communication system resilience. Space weather forecasting organizations provide early warnings, allowing industries to prepare for potential blackouts. Advancements like adaptive protocols and multi-band radios improve reliability, helping ensure stability in an increasingly interconnected and space weather resilient world. Risks to astronaut safety. Space weather poses a significant threat to astronaut safety, especially during missions beyond Earth's protective magnetosphere. Solar flares and coronal mass ejections release vast amounts of charged particles known as solar energetic particles, which can penetrate spacecraft shielding. These particles increase astronauts' risk of acute radiation sickness and long-term health issues, such as cancer. Even in low Earth orbit, such as aboard the International Space Station, radiation exposure rises during intense space weather events, though Earth's magnetic field provides partial protection. Astronauts face not only health risks, but also operational challenges due to space weather. Intense radiation exposure can impair cognitive function and decision-making, critical during emergencies or complex maneuvers. Radiation can also damage spacecraft electronics, leading to failures in navigation, communication, and life support systems. These malfunctions are particularly dangerous during extravehicular activities or critical mission phases, where even brief shielding failures could have catastrophic consequences. Missions to the Moon or Mars involve prolonged exposure to cosmic rays and solar storms, demanding innovative protective measures. During solar events, astronauts must quickly take shelter in heavily shielded compartments within their spacecraft. For surface missions, such as those planned on the Moon, underground habitats or shielding made from regolith are being considered to mitigate risks. To address these dangers, space agencies are developing advanced radiation forecasting systems and improved shielding materials. Personal dosimeters provide astronauts with real-time feedback on radiation exposure, enabling swift protective actions. By integrating these measures, space agencies aim to ensure that humanity's future explorers can safely undertake long-duration missions beyond Earth's natural protections. Effects on global navigation systems. Global navigation satellite systems, essential for modern technology, support applications ranging from GPS navigation to precision agriculture and disaster response. However, these systems are highly vulnerable to space weather events, particularly solar flares and geomagnetic storms. Charged particles from the Sun interact with Earth's ionosphere, causing rapid density fluctuations known as ionospheric scintillation, which distort satellite signals and reduce the accuracy of position, navigation, and timing services. During intense geomagnetic storms, ionospheric disturbances can cause satellite signals to lose lock or fail entirely, resulting in positioning errors that disrupt critical operations such as aviation landings, financial system synchronization, and precision-guided industrial machinery. These disruptions have ripple effects across multiple sectors, impacting both safety and efficiency. Military operations are especially vulnerable, with GNSS disruptions potentially leading to strategic disadvantages. Ground-based monitoring stations detect signal anomalies and provide corrective measures but cannot fully prevent temporary GNSS outages during severe space weather. Researchers are developing complementary technologies like terrestrial navigation systems and inertial navigation devices, which are less affected by ionospheric disturbances, to reduce GNSS dependency. Improved space weather forecasting offers early warnings, enabling industries to prepare for disruptions and maintain resilience in a space-dependent world. That concludes our journey through the incredible ways space weather affects Earth's technology. From disrupting satellites to posing risks to astronauts, these cosmic phenomena remind us of our planet's vulnerability and resilience. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, stay curious and keep exploring the wonders of science. Have you ever wondered how nature has inspired some of the most revolutionary technologies we use today? From the way birds soar through the skies to the microscopic strength of a spider's web, nature has been the blueprint for countless innovations. Imagine technology so ingenious that it mimics the way life itself solves complex problems. Join us as we uncover 10 groundbreaking everyday technologies inspired by nature's genius, revealing how the natural world shapes the modern one. Velcro and burrs. It's hard to imagine a world without Velcro, but its story begins in the Swiss Alps with an observant engineer and some pesky burrs. In 1941, Georges de Mestral noticed how these tiny seeds stuck to his dog's fur and his clothes during a hike. Curious, he studied them under a microscope and found a structure of tiny hooks that latched onto loops in fabric or fur. This natural mechanism became the inspiration for Velcro, a hook-and-loop fastener that revolutionized everything from clothing to space exploration. Today, Velcro is used in ways George could never have imagined. It's a staple in the fashion industry, allowing for quick adjustments and closures. It's also a hero in medicine, helping secure bandages and orthopedic devices. Even astronauts rely on Velcro in zero gravity to keep tools in place. What started as a nuisance in nature is now an essential tool for convenience and functionality. What's truly amazing is how Velcro shows the genius of biomimicry. By mimicking the simple yet effective mechanism of burrs, it transformed industries. It's a testament to the fact that nature often holds the answers to some of our most challenging design problems. Who would have thought that a hike in the woods could lead to such an invention? The next time you use Velcro, remember its origins in the wilderness. That simple burr, often dismissed as annoying, became the foundation for a technology that changed how we connect and secure things in our everyday lives. The Kingfisher and high-speed trains. The sleek design of Japan's Shinkansen, or bullet train, didn't just come from engineers, it was inspired by a bird. In the late 1980s, the train faced a noisy problem. Every time it exited a tunnel at high speeds, it created a loud tunnel boom due to air pressure changes. The solution? The Kingfisher is a bird known for its ability to dive into water without creating a splash. The team behind the train studied the bird's beak, which is shaped to minimize resistance. By redesigning the front of the train to mimic the Kingfisher's streamlined beak, they solved the noise issue and improved energy efficiency. The new design not only made the train quieter but also allowed it to travel faster while using less electricity. This innovation is a perfect example of how biomimicry can solve modern problems. Instead of forcing a solution, the engineers looked to nature, where millions of years of evolution had already perfected the design. The Kingfisher's ability to enter water seamlessly inspired a train that can cut through air just as smoothly. The next time you see a high-speed train zipping across the landscape, remember the humble Kingfisher? Its elegant dive didn't just inspire a quieter train, it showed how nature can offer solutions that are both efficient and beautiful. Shark skin and germ-free surfaces. Sharks are often thought of as terrifying predators, but their skin has inspired something that protects us: germ-resistant surfaces. Shark skin is covered with microscopic, tooth-like structures called dermal denticles. These ridges reduce drag in water, allowing sharks to move efficiently. But scientists discovered something else. These ridges prevent bacteria from clinging to the surface. This discovery led to the creation of sharklet, a surface material that mimics the texture of shark skin. It's used in hospitals where preventing bacterial growth is critical. Unlike traditional antibacterial coatings, sharklet doesn't rely on chemicals. It physically stops bacteria from latching on. This makes it a safer, more sustainable option for healthcare and hygiene. The applications of this technology extend beyond hospitals. It's being explored for use in public transport, schools, and even kitchens, where cleanliness is paramount. By studying a creature that has survived for millions of years, scientists developed a material that could reduce infections and improve sanitation worldwide. It's incredible how something as primal as shark skin can inspire modern solutions. The next time you think of sharks, consider their role in making the world a cleaner, safer place, not just as predators, but as protectors. The lotus leaf and self-cleaning surfaces. The lotus leaf, known for its beauty and symbolism in many cultures, is also a marvel of natural engineering. Its surface is covered with tiny bumps that repel water and dirt, keeping it spotless even in muddy ponds. This phenomenon, known as the lotus effect, inspired the development of self-cleaning surfaces. Scientists replicated this effect to create coatings for windows, solar panels, and even fabrics. These surfaces repel water, causing it to bead up and roll away, taking dirt with it. It's an innovation that saves time, reduces maintenance, and even extends the lifespan of materials. Imagine windows that clean themselves every time it rains, or solar panels that stay efficient without manual cleaning. The lotus effect goes beyond convenience. It reduces the need for harmful cleaning chemicals, making it an environmentally friendly solution. From skyscrapers to personal gadgets, the applications of this technology are limitless. It's a perfect example of how nature can inspire sustainability and efficiency. Next time you see rain sliding effortlessly off a surface, think of the lotus leaf. What seems like a simple natural process has inspired a technology that's transforming industries and reducing our environmental impact. Gecko feet and super adhesives. Geckos are nature's climbing champions, effortlessly scaling walls and ceilings. Their secret lies in the microscopic hair-like structures on their feet called setae, which create a weak molecular attraction known as van der Waals forces. These forces allow geckos to grip surfaces without using suction or glue, making their ability both strong and reusable. This natural mechanism inspired the creation of super adhesives that mimic gecko feet. Unlike traditional adhesives, these materials are reusable and leave no residue behind. They are used in robotics, allowing machines to climb walls and ceilings just like geckos. Even in the medical field, gecko-inspired adhesives are being developed for wound care, providing a secure yet painless alternative to stitches or staples. What makes gecko-inspired adhesives so fascinating is their potential for future innovations. From helping astronauts stick tools to the walls of spacecraft to creating reusable household items like wall hooks, the possibilities are endless. By understanding the science behind the gecko's grip, engineers are creating solutions that are both practical and eco-friendly. The next time you see a gecko defying gravity, remember that its tiny feet have sparked a revolution in adhesives. It's proof that even the smallest creatures can inspire some of the biggest breakthroughs. Spider silk and strong, lightweight materials. Spider silk is nature's ultimate multitasker. It's stronger than steel by weight, more flexible than synthetic fibers, and incredibly lightweight. Spiders use it to build webs, catch prey, and even protect their young, making it one of the most versatile materials in nature. Scientists have long been fascinated by spider silk's unique properties. By studying its molecular structure, researchers have developed synthetic versions of spider silk for various applications. These include bulletproof clothing, lightweight ropes, and even biodegradable sutures in medicine. The material's strength and flexibility make it ideal for industries ranging from defense to healthcare. What's even more exciting is how spider silk is being produced. Instead of farming spiders, researchers use bioengineering to produce silk proteins in bacteria, yeast, or even plants. This method makes it scalable and sustainable, ensuring that nature's design can benefit modern technology without harming ecosystems. Spider silk isn't just a natural marvel, it's a glimpse into the future of materials science. Whether it's protecting lives or improving sustainability, the humble spider is helping us weave a better world. Termite mounds and climate-controlled architecture. Termites, often seen as pests, are actually master architects. Their mounds, found in some of the world's hottest regions, stay cool inside even when temperatures outside soar. This is due to their ingenious natural ventilation system, which circulates air and regulates temperature without using energy. Inspired by termite mounds, architects have developed buildings with natural cooling systems. One famous example is the Eastgate Center in Zimbabwe, a shopping complex that uses passive cooling inspired by termite mound design. The building consumes less than 10% of the energy used by traditional air-conditioned structures, proving that biomimicry can be both innovative and sustainable. The termite-inspired design isn't just limited to commercial buildings, it's being applied to homes and offices, helping reduce energy consumption and carbon footprints. By learning from these tiny insects, we're creating spaces that are not only comfortable but also environmentally friendly. The next time you hear about termites, think of them as nature's green architects. Their remarkable structures are paving the way for energy-efficient designs that could reshape our built environment. Whales and wind turbine efficiency. Whales, especially humpbacks, are massive yet surprisingly agile swimmers. Their fins are equipped with unique bumps called tubercles, which help reduce drag and improve lift. This adaptation allows whales to maneuver gracefully through water despite their size. Engineers have applied this principle to wind turbines, redesigning their blades to mimic the tubercles on humpback whale fins. The result is a more efficient turbine that generates more energy, even in low wind conditions. These biomimetic blades are not only improving renewable energy production, but also reducing the environmental impact of wind farms. The whale-inspired design doesn't stop at wind turbines, it's also being explored for airplane wings, underwater vehicles, and even sports equipment like surfboards. By copying nature's efficient designs, we're finding smarter ways to interact with the elements. The next time you see a wind turbine spinning on the horizon, think of the humpback whale. Its elegant fins have inspired a cleaner, greener future for energy. Butterfly wings and color without pigments. Butterfly wings are dazzling not just because of their colors, but because of how those colors are created. Instead of using pigments, butterfly wings rely on microscopic structures that reflect and bend light, producing iridescent hues. This natural phenomenon, called structural coloration, is both vibrant and long-lasting. Inspired by butterfly wings, scientists have developed materials that mimic this structural coloration. These are used in everything from cosmetics to high-tech displays and even security features on currency. Unlike traditional dyes or pigments, these materials don't fade over time, making them more durable and environmentally friendly. The applications go beyond aesthetics. Structural coloration is being explored for energy-efficient displays, where colors are produced without backlighting. It's also being used in textiles to create fabrics that change color under different lighting conditions, opening up new possibilities in fashion and design. The brilliance of butterfly wings shows how beauty and functionality can go hand in hand. They remind us that even the smallest details in nature can inspire transformative technologies. Woodpeckers and shock-absorbing technology. Woodpeckers endure thousands of impacts daily as they peck at trees, yet they don't suffer brain injuries. This is thanks to their unique anatomy, which includes a spongy bone structure in their skull and a specialized beak that absorbs shock. Inspired by woodpeckers, engineers have developed shock-absorbing materials for helmets and protective gear. These materials mimic the bird's ability to distribute impact, providing enhanced safety for athletes, construction workers, and even military personnel. Woodpecker-inspired designs are also being used in technology. For example, they've influenced the development of shock-proof casings for delicate electronics and sensors for space exploration. By studying how these birds handle extreme forces, researchers are creating innovations that protect both people and devices. The next time you see a woodpecker at work, think of its role in advancing safety and technology. Its remarkable resilience has inspired solutions that keep us safe in some of the most challenging environments. That wraps up our exploration of 10 everyday technologies inspired by nature's brilliance. From gecko feet to butterfly wings, these innovations show how closely connected we are to the natural world. If you enjoyed this journey into biomimicry, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep discovering the wonders of nature and science with us. Have you ever wondered how stars, those dazzling points of light in the night sky, come into existence? What fuels their brilliance and what becomes of them when their time runs out? The life of a star is a mesmerizing journey through creation, destruction, and rebirth. From their celestial cradles to dramatic final acts, stars play a crucial role in shaping the universe. Join us as we unravel the fascinating life cycle of stars, from their birth to their cosmic legacy, in this journey of awe and wonder. Nebula, the birthplace of stars. The journey of a star begins in a nebula, a vast cloud of gas and dust that serves as the cradle of star formation. Spanning light years, these dynamic regions are full of movement and energy, where gravity gathers raw materials to create the points of light we see in the night sky. Nebulae vary in type and behavior, with each offering unique characteristics. Emission nebulae glow vividly, often in red or pink as their gases are ionized by nearby young stars. Reflection nebulae appear faintly blue, scattering starlight like a cosmic mirror. Dark nebulae, in contrast, block starlight, creating shadowy voids that intrigue astronomers. Iconic examples like the Eagle Nebula's pillars of creation showcase the beauty and complexity of these stellar nurseries. Gravity is the driving force behind star formation, gradually condensing regions of the nebula over millions of years. As particles draw closer together, they form dense clumps called protostellar cores, where gravitational energy converts into heat. These cores begin to radiate faint light, marking the initial stages of a star's development. Not all regions within a nebula will form stars. Some lack the necessary mass to trigger nuclear fusion. However, those that succeed undergo a spectacular transformation, growing hotter and denser until fusion ignites. Once this process begins, a star is born, leaving its nebula behind. The nebula, though left behind, often continues to influence its surroundings, enriching the cosmos with elements for future stars and planets. Every star in the night sky reminds us of its humble beginnings within these breathtaking cosmic nurseries. Protostar, the star awakens. The journey from a nebula to a star continues with the formation of a protostar, a dynamic and transformative stage in a star's life cycle. A protostar is a nascent celestial body still gathering mass and energy, striving to ignite the fusion reactions that will define its stellar existence. Though not yet a fully formed star, the protostar glows faintly from the gravitational energy of its collapsing core. This phase begins when regions within a nebula become dense enough for gravity to pull surrounding gas and dust inward, forming a spinning disk of material around the developing protostar. The rotation of this material results from the conservation of angular momentum, causing the collapsing matter to spin faster and transform dramatically. As gravitational forces compress the protostar's core, its temperature rises to millions of degrees, producing the faint but growing glow that signals its progress. Surrounding the protostar is the protoplanetary disk, a ring of leftover material that may eventually form planets, moons, and other celestial bodies. This stage is not just crucial for the star's birth, but also for the potential creation of planetary systems. The protostar's environment is turbulent, with magnetic fields and jets of energy interacting with the surrounding material. These jets can expel excess matter, clearing space and shaping the cosmic landscape. The pivotal moment comes when the core's temperature and pressure rise high enough to trigger nuclear fusion. Hydrogen atoms fuse into helium, releasing immense energy and stabilizing the star by balancing gravitational collapse with outward radiation pressure. At this point, the protostar transitions into a main sequence star, leaving behind its turbulent beginnings. The protostar phase is a fleeting yet crucial chapter, bridging the gap between the diffuse clouds of a nebula and the radiant brilliance of a star. Each protostar tells a story of resilience and transformation, a celestial tale inscribed in light, gravity, and the boundless creativity of the cosmos. Main sequence: the star's prime. Every star eventually reaches its prime, and this phase is known as the main sequence. During this stage, a star achieves a delicate balance between the outward pressure created by nuclear fusion and the inward pull of gravity. For many stars, this period is the longest and most stable phase of their lives, often lasting billions of years. The main sequence is where stars truly shine, both figuratively and literally, as they radiate energy and light into the vast expanse of the cosmos. The main sequence begins once a star's core temperature becomes hot enough to sustain nuclear fusion. This process primarily involves hydrogen atoms fusing into helium under extreme heat and pressure, releasing an immense amount of energy. This energy radiates outward, counteracting the force of gravity that constantly tries to collapse the star. The result is a star that maintains a stable size, temperature, and luminosity. The exact characteristics of a star during this phase depend on its initial mass. Massive stars burn through their fuel more quickly, shining brighter and hotter, while smaller stars like red dwarfs burn more slowly and steadily. For our Sun, the main sequence has been a time of relative calm and stability, lasting about 4.6 billion years so far. It is during this phase that a star provides the conditions necessary for planets to form and in some cases life to emerge. The energy emitted by main sequence stars drives weather systems, sustains ecosystems, and fuels the chemical reactions that shape planetary environments. The Sun's predictable and steady output of energy is a hallmark of its time on the main sequence, creating the perfect conditions for life to thrive on Earth. However, the main sequence is not an eternal state. As stars consume their hydrogen fuel, the composition of their cores begins to change. Over time, helium accumulates in the core while hydrogen-burning reactions shift to the outer layers. This gradual change in composition marks the beginning of the end of a star's main sequence phase. The exact duration and manner in which a star leaves the main sequence depends on its mass. Smaller stars may linger for trillions of years, while massive stars burn out in just a few million years. The main sequence phase is a star's golden age, a time when it achieves the stability and brilliance that define its character. It's the period during which stars contribute the most to their galaxies, providing light, heat, and the essential conditions for the birth and evolution of planets. For stars like our Sun, it's a reminder that even the most luminous and powerful entities in the universe experience a life cycle, moving from birth to maturity and eventually toward transformation. The main sequence is a celebration of energy, balance, and the sheer beauty of starlight in the cosmic arena. Red giant or supergiant, the expansion. When a star exhausts the hydrogen in its core, it undergoes a dramatic transformation, expanding into a red giant or supergiant. This phase marks the transition into its twilight years, where the star's size and brightness increase while its core experiences intense changes. Once stable, the star begins a journey of instability and grandeur, signaling the beginning of its eventual end. Depending on its mass, it will either become a red giant, like our Sun will someday, or a supergiant if it began life with significantly more mass. The transformation starts when hydrogen fusion ceases in the core, causing it to contract under gravity. This contraction raises the core's temperature and pressure, igniting hydrogen fusion in a shell around the core. The resulting outward pressure forces the star's outer layers to expand dramatically, cooling in the process and giving the star its reddish hue. A red giant can grow to hundreds of times its original size, while a supergiant can become thousands of times larger. For red giants, this phase often involves the fusion of helium in the core, creating heavier elements like carbon and oxygen. In supergiants, the process is more extreme, with layers of fusion producing elements up to iron. Red giants often create planetary nebulae, glowing shells of gas that surround the dying star. Supergiants, on the other hand, undergo more violent ejections, setting the stage for supernova explosions. The red giant or supergiant phase is a breathtaking chapter in cosmic evolution, showcasing the immense power of fusion and the impermanence of even the mightiest stars. These expanded stars are not only visual marvels but also key contributors to the chemical enrichment of galaxies. Their transformation is a testament to the universe's creativity and a reminder that even the most brilliant stars are finite, destined to evolve and pave the way for new generations of celestial wonders. Supernova or planetary nebula, the grand finale. The end of a star's life is a dramatic and breathtaking spectacle, culminating in either a supernova explosion or the delicate beauty of a planetary nebula. This grand finale is determined by the star's mass, marking its transition from a radiant celestial object to its final form. Stars with low to medium mass like our Sun end their lives more gently, creating planetary nebulae, while massive stars erupt in supernova explosions, scattering the elements they forged into the cosmos. For stars like the Sun, the journey toward a planetary nebula begins as they shed their outer layers during the red giant phase. Over thousands of years, these layers are expelled into space, forming glowing shells of gas and dust illuminated by the hot, dense core left behind. These planetary nebulae, with their stunning shapes and colors, are some of the most mesmerizing sights in the night sky. The material they release carries elements like carbon and oxygen, enriching the interstellar medium and contributing to the formation of new stars and planets. Massive stars, on the other hand, take a far more explosive path, leading to a supernova. When the core of a massive star runs out of fuel, it collapses under gravity, releasing an immense amount of energy in an instant. This collapse triggers a shockwave that tears through the star's outer layers, creating a supernova so brilliant it can outshine an entire galaxy for a brief time. Supernovae are not just explosions, they are cosmic forges creating elements heavier than iron such as gold and uranium in their intense heat and pressure. The remnants of a supernova can form a neutron star, or if the original star was massive enough, collapse further into a black hole. These outcomes leave behind some of the most enigmatic objects in the universe, continuing to shape the cosmos in their unique ways. The grand finale of a star's life, whether as a planetary nebula or a supernova, is a reminder of the cosmic cycle of creation and destruction. From dazzling nebulae to the awe-inspiring power of supernovae, these endings are not just conclusions but the beginnings of something entirely new in the vast expanse of space. White dwarf neutron star, or black hole, the final form. When a star reaches the end of its life cycle, it transforms into one of three final states: a white dwarf, a neutron star, or a black hole. These outcomes represent the star's ultimate stage of evolution, and are determined by its initial mass, revealing the universe's incredible extremes and contributions of stellar remnants to the cosmos. Stars like our Sun, with relatively low to medium mass, end their lives as white dwarfs. After shedding their outer layers as planetary nebulae, their cores remain as dense, Earth-sized objects composed mostly of carbon and oxygen. Though fusion ceases, these remnants emit faint light from residual heat, cooling slowly over billions of years. Over time, white dwarfs may crystallize, forming a giant cosmic diamond. Massive stars, however, often end as neutron stars. When such a star undergoes a supernova, its core collapses under immense gravitational pressure, compressing into an object just a few miles across. Despite their small size, neutron stars can weigh up to 1.4 times the Sun's mass, and are composed almost entirely of tightly packed neutrons. Some neutron stars spin rapidly, emitting beams of radiation detectable as pulsars. For the most massive stars, the collapse of the core after a supernova can lead to the formation of a black hole, an object with gravity so intense that not even light can escape. Stellar black holes formed from stars at least 20 times the Sun's mass represent the ultimate extremes of space-time, where known physical laws break down. These objects shape galaxies and provide insight into the boundaries of physics. The final form of a star, whether a white dwarf, neutron star, or black hole, is a captivating chapter in its story. These remnants preserve the legacy of their parent stars, while enriching the dynamic and interconnected cosmos, highlighting the universe's boundless creativity and complexity. The cosmic legacy of stars. Stars are not merely celestial bodies lighting up the night sky. They are the architects of the universe, leaving a profound legacy that shapes everything we see around us. From the elements that compose our bodies to the vast structures of galaxies, stars influence the cosmos far beyond their lifetimes. The story of stars is deeply intertwined with the universe's history, making their legacy a cornerstone of cosmic evolution. At their core, stars act as cosmic forges, creating elements through nuclear fusion. In the intense heat and pressure of their cores, hydrogen fuses into helium, releasing immense energy. As stars age, this fusion forms heavier elements like carbon, oxygen, and even iron in massive stars. When stars end their lives in supernovae, they scatter these elements across space, seeding future stars, planets, and life itself. The remnants of stars also contribute to the cosmos, forming dense neutron stars, mysterious black holes, or expansive nebulae after their deaths. Nebulae in particular become stellar nurseries, where gas and dust from one generation of stars coalesce to form the next. This cycle of birth, life, and death underscores the dynamic nature of the universe. Perhaps the most remarkable aspect of a star's legacy is its role in enabling life. Without the elements forged in stars, planets like Earth could never have formed, and life as we know it would not exist. Stars are more than points of light. They are the universe's storytellers, shaping the past, present, and future. Their influence continues to resonate across space and time, ensuring their story lives on. That wraps up our exploration of the life cycle of stars, from their stunning beginnings in nebulae to their grand legacies as cosmic creators. If you enjoyed this stellar journey, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the universe and reaching for the stars with us. Did you know that the sun's activity can disrupt power grids, knock out satellites, and even endanger astronauts? From massive solar flares to powerful geomagnetic storms, space weather has an extraordinary impact on our modern world. But what exactly happens when the cosmos decides to unleash its fury? Join us as we dive into 7 astonishing ways space weather shapes and challenges Earth's technology, revealing a hidden force we rely on but often overlook. Satellite communication disruptions. Satellite communication systems are highly vulnerable to space weather, with solar flares and coronal mass ejections posing significant threats. High-energy particles and electromagnetic radiation from these events can interfere with the radio waves satellites use to communicate with Earth. Disruptions caused by solar storms can affect television broadcasts, internet services, and GPS navigation. These interruptions create cascading effects in industries reliant on real-time data, including aviation and maritime operations. For instance, navigation systems may become inaccurate during solar storms, leading to delays and safety concerns. The physical infrastructure of satellites also faces risks from charged particles during solar storms. These particles can accumulate on satellite surfaces, causing short circuits and damage to onboard systems. Operators often place satellites in safe mode during heightened solar activity to protect sensitive components. While this precaution minimizes damage, it halts the satellite's operations temporarily, impacting services like telecommunications and weather forecasting. Prolonged space weather events can accelerate satellite degradation, weakening materials, and reducing solar panel efficiency. Such degradation shortens satellites' lifespans, raising economic and operational concerns as the world increasingly depends on satellite networks. Past geomagnetic storms have caused millions of dollars in satellite damage, highlighting the stakes involved. To counter these risks, advanced monitoring systems and better satellite designs are critical. NASA and NOAA track solar activity to provide early warnings, helping operators prepare. Radiation-hardened materials and enhanced shielding are also improving satellites' resilience, ensuring uninterrupted global connectivity despite space weather challenges. Power grid failures. Power grids are among the most vulnerable systems to the effects of space weather. Geomagnetic storms caused by solar activity can generate geomagnetically induced currents in the Earth's crust. These currents infiltrate power grids, overloading transformers and disrupting their functionality, leading to widespread blackouts, as seen during the 1989 geomagnetic storm that caused a 9-hour outage in Quebec, Canada. The infrastructure of power grids experiences significant stress during geomagnetic storms, especially transformers, which are crucial for electricity distribution. Overheating and physical damage from induced currents can cause transformer failures, increasing the risk of cascading outages that can spread across regions. The risks are heightened in polar regions, where geomagnetic effects are stronger due to proximity to Earth's magnetic field lines. Power grid failures have far-reaching consequences beyond immediate outages, impacting essential services like hospitals, communication networks, and transportation systems. Prolonged disruptions can result in financial losses and safety risks for affected populations. The integration of smart grids and renewable energy sources adds complexity, amplifying the challenges of maintaining grid stability during geomagnetic storms. To mitigate these risks, scientists and engineers focus on real-time monitoring of solar activity and geomagnetic conditions, providing utility operators with early warnings. These alerts allow preventive measures such as adjusting grid load or shutting down vulnerable systems to be implemented. Advancements in transformer design and protective technology, like geomagnetic storm detectors, further enhance grid resilience, ensuring reliable electricity despite space weather challenges. Satellite damage and orbital hazards. Satellites, essential for modern communication and navigation, are highly vulnerable to space weather. Energetic particles from solar storms can penetrate a satellite's shielding, causing malfunctions in electronic components and disrupting services like GPS navigation, internet access, and global communications. A significant example occurred in 1994, when a major solar storm caused multiple communication satellites to malfunction, leading to widespread service outages. Radiation from solar activity further challenges satellites by degrading construction materials over time. This exposure weakens solar panels, reducing power efficiency and shortening operational lifespans. Intense solar events can also trigger damaging electric discharges within satellites, potentially rendering them inoperable. These risks highlight the need for rigorous testing and innovation in satellite design to ensure resilience against space weather.